present his work on non-random matching in an evolutionary model of playing general games. So it's not restricted to a particular example. He's going to present it in terms of the prisoner's dilemma, but this is a result that applies to general games. I'm going to briefly discuss his work. Then we have Herb talk to us about human-specific evolution. And finally, we're going to finish with a discussion of Dirk's model of the evolution of cooperation, and hopefully this will lead to a more general discussion about preferences again and different evolutionary models. So, thank you very much.
Thanks very much for the invitation and for the organization of this workshop. This paper is joint work with my supervisor, Martin Jensen, in the University of Leicester. And it's an evolutionary model. It's theoretical. No applications here. No empirics. And it's going to be very much like Heinrich's model in the sense that we're going to be looking into matching. And, well, but in a much more general way for broader games than just go along. Cool. So, what is the aim of this paper? The aim is to provide an equilibrium concept that can capture arbitrary non-random matching in evolutionary models. Okay, so standard results have been using random matching between agents in a big population. We're trying to generalize that and to formalize that. And also we want to look into welfare under these kinds of non-random matching models. Okay, so let's start. The story starts with evolution. The idea of evolution starts with Darwin, as we probably all know. And the motto is the survival of the fittest. Right? This is very stylized, it's not exactly true, but the idea is that, well, if fitness is a expected number of children individuals get, then if you have more children, your kind of gene is going to replicate faster, right? It's going to take over the population. So successful strategies in a specific environment will tend to take over the population. Right? Now, what is the problem, as we've seen, right? So there's a puzzle that we see cooperative behavior, and so if natural selection favors the fittest, then cooperative behavior or cooperative traits should have been wiped out of existence long ago. Yes, please.
And here I would disagree.
Okay.
Because, fittest means like better adapted to the environment, right?
True.
So it totally depends on the environment whether cooperative behavior is beneficial or not, right?
Excellent. But when we say cooperative here, we think usually of cooperating in a prisoner's dilemma, which is a strictly dominated strategy. And this is a very good question, because actually this is what is going to matter in the end, right? And this is what we're going to see. We're going to have assortative matching, or any kind of matching, and that will change what will be beneficial. This will change the dynamics.
Think of this as, this is something that some people have said. Some people have
Oh,
said.
sure, yeah.
Okay, so it's just...
Okay. Right, but of course we observe cooperative behavior, so how did that happen? How did that come to survive? Of course, the main concept of evolutionary game theory, an evolutionary stable strategy, is a Nash Equilibrium refinement. So it can help us as defect is a dominating strategy in the prisoner's dilemma. Right? So it's not enough. We need something more. One answer to that is non-random or assortative matching. So by that we mean if there is a higher chance for cooperators to meet cooperators than defectors to meet cooperators, that can give an evolutionary advantage to cooperators, and cooperation can basically survive, right? Or take over the whole population. But we're going to look into that more specifically. Right, let me review the literature a bit. Assortative matching can occur with different mechanisms behind it. Here we're going to be very agnostic. We don't know what the mechanism behind it is, but let's review some examples. Assorted matching kind of happen because of kin selection. So when the environment is such that individuals interact mostly with the kins, right? With the kin. Local interactions, as in models, as in the model we saw, Dirk's model on Wednesday, right? So you have a neighborhood and you mostly interact with your neighborhood, and that can give some kind of assortative matching. The green beard effect, which means that if individuals can tell who they're interacting because they have a green beard, right? So cooperators have a green beard. Oh, I can tell this guy's a cooperator, I'm a cooperator, I'll match with him and get better payoffs. Also, it can be it can occur by homophily. So I like to be with people that are like me, right? And maybe we share the same genes, and that can help cooperation. Or meritocratic matching, as Heinrich presented on Wednesday. So there's somebody who assorts actions according to cooperation. So more cooperative people will tend to meet more cooperators. Right, so first, to my knowledge at least, formal kind of assortativity model was introduced by Bergstrom, and he looks into exactly that. What we're trying to do is to study that in a much broader sense. So introduce a broad equilibrium concept that can capture non-random matching, and to provide welfare theorem for evolutionary models with non-random matching. Right? So we want to be broad and we want to be optimistic. So let me introduce you the model. So the model ingredients are going to be a normal form game. Think of that as a prisoner's dilemma to begin with. But it's much more general, as you will see. And so we have a normal form game, which is M player, M strategies, so it's general. And a matching rule. So the normal form game dictates how individuals get payoffs or fitness. For us, it's going to be the same. So we're looking more or less, I think we're looking into home economics. But assortative matching can occur because of social preferences, maybe. And the matching rule will dictate how people are going to be matched to each other according to the strategies. Right? So it is an action matching. Okay, so we start with a large population. So we don't have a discrete population as you've seen in previous models. So now we have a continuum, going to be the interval from 0 to 1. Right? And they will be playing an n-player, n-strategy symmetric normal form game. And what do we mean by that? It's a symmetric game. People get payoff independently of who plays what. The only thing that matters is how many people in your group, right? How many people follow each strategy. It doesn't matter who. Right? So this is symmetric. Now, if you think of that in such a symmetric normal form game, there will be that many different types of groups. And what do I mean by types? Is that, okay, if you have 2 players and 2 strategies, as in the prisoner's dilemma, for example, you can have only 3 groups. Okay, you can have a group number 1, which has 2 people, 2 cooperators, and 0 defectors. You can have group number 2, has 1 cooperator and 1 defector, and group number 3 has 2 defectors. Right? I mean group type. If you have two players, 3 strategies, then you have these groups, right? And this indicates how many people are in follow strategy 1, how many people follow strategy 2, how many people follow strategy 3 in the group. Okay, so these will be the group types, and we have M strategies. So all we need is a matrix. I mean, we need these elements that tell you if you're an a J type in an I type group, how much payoff you're going to get, how much fitness individuals are going to get, right? So this is enough to summarize a normal form game. But for this presentation, think of the prisoner's dilemma. We're in this case, 3 groups. Right. Yeah, okay. This is the big. Now, the dynamics, how the system evolves. We have a state of the world, which is how many, each x is the proportion of people that follow each strategy, right? So x1 is the proportion of people that follow strategy 1, and so on. Okay. At each state, so you can think of that either in continuous or in discrete time, the results are going to be the same. Now, all agents are drawn into groups, so they form n-size groups. And they do not choose the strategies. We're going to start from an evolutionary kind of thing. They have genes that code for behavior. Then we're going to make them a bit smarter. But we'll start from them being stupid, right? Homo stupidus. So they will just follow the strategy they were meant, they coded by the genes to follow. Now, they're drawn into groups. All of the population is drawn into groups, and then they follow the strategies that they were meant to follow, and they get payoffs based on that. They get payoffs in terms of fitness, and fitness is interpreted as an expected number of children that this individual will get. After that, all children adopt their parents' behavior, right? And then we aggregate the children population, parents die, and we have the population at the next stage. Okay, what I did not tell you is how individuals are drawn into groups, which is what we're going to look into now. Right? So we have a matching group. So it tells you how individuals are drawn into the groups, how from a continuum of population get into a continuum of groups. So it gives a proportion of total groups that are of type pi for each state of the world, right? For any given mixture of population. So the definition is that the matching rule is a function that maps population distributions to group distributions. And you may want to think, well, I kind of have to do some accounting here, right? I need to have, if there were 5 people in the original population, then I would need to have, 5 nice people in the original population, I would need to have 5 nice people matched into the groups. So we can impose a consistent matching rule. There is a condition for that, but I'm not going to bother you with the math. You may want to impose that, but you can also see more general matching rules that will make sense a bit later in one of our applications. So a group selection model will have a normal form game and a matching. So these are our building blocks. Okay. Now let me give you an example. Think of the prisoner's dilemma here. Let's say that the white dots are individuals that cooperate and the black dots are individuals that defect. So if the state of the world is X, so that means that the proportion of X1 are cooperators and the proportion X2 are defectors, then F is a vector, right? So the first coordinate of F will give you the proportion of groups of type 1 after the matching has occurred, and so on for the rest of the 2. And let me give you an example of 2 matching rules. Probably the easiest to think of is the random matching, right? So you will have a proportion of x1 squared of groups that are of cooperator to cooperator, 2x1, x2 mixed groups, and well, x2 squared groups that are containing 2 defectors. In the opposite, in the exact, well, not the exact opposite, in another case, when you have complete segregation, you can think that, well, there is nobody here, there are no mixed groups, cooperators only match with cooperators, defectors only match with defectors. And these are the fitnesses. You can see that there are some things that we cannot define, but that's fine. Yes?
Can you provide some intuition as to
why this would be a useful model of a matching rule. What might this correspond to in the real world? Because I can imagine other matching rules that are based on spatial, and that has some intuition. But this one seems to be very abstract in the sense that there's a population that defines.
This one, the complete segregation one?
But I mean, it's a general approach.
Oh, this can be anything. It can be anything you can imagine. I mean, these functions can be whatever you can fit. Any process would lead to a proportion of groups being of each type.
Okay, maybe a more blunt way to ask the question is, what is this a model of?
What is this? Of evolutionary processes to begin with. And you can see that using that we can get results for even kind of complicated models such as the trade group model. So we can use that, we actually get results there. And it's good we can do comparative statics doing that, and we can give a nice theorem, well, the optimistic theorem, almost optimistic, of how we can get good welfare. Hopefully I'll convince you. Yeah. So, well, think of an agent that follows strategy J. Forget about that. This is, well, it's a proportion of J individuals that are found in I-type groups, and this is the payoff they get. So if you sum over them for all groups that they're in, you will get the expected payoff, right? So the expected fitness. So let's try to make them a bit smarter now, our individuals, and let's let them think strategically, right? So if they think they will, well, may play, I mean, the whole economic is so they will play Nash Equilibrium. And they know the state of the world. If they know the state of the world, well, let them not know. They know the matching rule. That's the only thing they know, right? So they will try to maximize their expected payoff. They will try to find a vector Y, on how to mix among the strategies such that they maximize the payoff. Based on that, we can define a Nash equilibrium of that game, right? Under that matching rule, which we call a Nash equilibrium with group selection. And I know I just said a bad word, but I'll try to talk about group selection a bit later. So, what is a Nash equilibrium under group selection? Well, it is if you use that mixed strategy and the rest of the population uses the same mixed strategy, you cannot do any better, right? You cannot have a positive deviation, beneficial deviation. And also based on that, we can define an evolutionarily stable strategy of that game, so, which we call evolutionarily stable strategy under group selection, which means that if, in case that anybody, so if you have a uniform population that uses that strategy, and it was invaded by another population using some other strategy, the incumbent strategy would still do better than the invader. Right? So this gives a stability, like dynamic stability. Okay. Now I'm going to connect that with group selection models. So what is the idea of group selection? The main idea, and has been very criticized in the biology literature, it says that, well, groups that do better maybe will outperform those with lower fitness, right? So groups that fare better can replicate faster, and that can kind of give chances for cooperative behavior to survive. And this has been studied. I mean, the most formal model, first formal model is made at Smith, and also studied by Wilson, and has been analyzed in more economic kind of sense from Cooper and Wallace. So let me give you a story here. What happened is there. So we still have a continuum population. In our formulation, we have continuum population. So it has to be consistent with the rest of the theory. Individuals can be either cooperators or defectors. They play a prisoner's dilemma. And they're randomly matched to form trait groups of size 2. Now we have fixed size 2, and we have the random matching rule. They normally, randomly get drawn into form groups of size 2. They interact in the trait group, so the pairs interact with each other. They get fitness as an expected number of children, and they get their children. Right? But the children will remain in each of these groups. So these groups are separated, and they will not interact for a few generations. Right? So they will stay there, and then next round they're going to be randomly matched among them. Will get children, and these will stay in the original trait groups. So this happens for T generations, and after the T generations have gone through, then the whole population gets together again. And we try to study how, in that dispersion phase, when they're all getting together, what's happening there? What is the population mixture? Sure.
Just a question. So the children remain in the trait group?
Yes.
For how long?
For T generations. So let's say you have two people, right? So a cooperator and a defector, right? And the cooperator gets 2 children, the defector gets 10. Right? They have 10 defectors and 2 cooperators there. They're going to be randomly matched among them to get other pairs. These are going to interact, they're going to get payoffs, and the children will still remain in that group. So that will be generation 2, then you have generation 3, and so on. And T is given, it's exogenous, right? So we say, let's see if they stay there structured for how long. This is exogenous. I mean,
I'm kind of then also, because I think probably this T, the implementation of T is probably crucial.
Yeah, sure. Let's assume that there's a natural process there. It's not my model, is it?
Yeah.
But it's of course, it may not be the same for everybody. And then the process repeats itself. So we can prove a proposition here. Well, if you have a T-period trait group model, then we can find a matching rule. This will not be consistent necessarily, such that the dynamics and the steady states of the group selection model coincide with the dynamics and steady states of the trait group model. Okay? So basically we can use the matching rule idea, a model, to study these groups, these models, and I'll show you the results. Right, now, very simple results that are probably very intuitive, make sense if you've read a bit of evolutionary game theory. Existence of equilibrium under some conditions, continuity and smoothness. It's continuity basically. There always exists a Nash equilibrium under group selection for every kind of matching. Then steady states, it tells you that all Nash equilibria under group selection are steady states of the system, but under the random matching rules, if you use the random matching rule, is what we expect. You get Nash equilibrium basically, right? And ESS as we know. So these are kind of to show that our concepts are consistent with existing theory.
I think this is important. So with random matching, you can only select from the Nash equilibria that this normal form game gives you. You cannot do better.
Yeah. You get exactly that, and you get all of them. And there are other results here that this is again bookkeeping. It just shows that these are consistent to some extent with existing literature. There are a few theorems that are hold here, but it's about stability, and yeah, I think it's about stability. Now, buffer. So let's think of the following thing, right? We have a normal form game, and we have matching rules. And we think of the set of all states and all matching. So we have all states under any matching rule, right? And we try to find which of them are steady states. Now, there will be one that's going to be best, right? Or best among equals, right? So this we will call an evolutionary optimum. And there we have the Werfer theorem. We say that if we find that evolutionary optimum, for any evolutionary optimum, we can find a matching rule that implements it as a Nash equilibrium under group selection. So this is kind of the optimism. Now, we have a that. Let's go into applications. You see that applied. Right, I'm going to use just the prisoner's dilemma. It can be used very much more broadly. But here, because I think this is what we've talked about throughout the conference, I think this is interesting. Right, so, and I'm going to study a very specific set of matching rules that have a constant index of associativity, introduced by Bergström. So that means that it is more likely for cooperators to meet cooperators than defectors to meet cooperators, and the gap between the two probabilities is constant for any population state, right? For any state of the world. And for prisoner's dilemma games like this one, where the CD outcome is less, the sum of fitnesses here is less than the sum here and there. What does that mean? So if I have 4 people, I'd rather have 2 of them cooperate and 2 of them defect. And I'd rather, so if I have 2 cooperators and 2 defectors, I'd rather match the 2 cooperators together and the 2 defectors together. That gives a higher payoff, rather than having 2 mixed groups. Right? This is what this condition means. Dynamics look like that. If associativity is 0, then we have, this is dynamics, right? So this is x, and this is x dot. It's a time derivative of the population state. And this is the proportion of individuals that are cooperating. So dynamics, you can see it's always negative, so I always have to go back when associativity is 0, which is the same for point 2 and point 4. When you get to point 6, this brings you back, and this brings you forward. So you can find, this brings you back, and this brings you forward. So we have 3 Nash equilibria, 1 here, 1 there, right? And 1 in the middle. We have a mixed Nash equilibrium, which is not stable. This is unstable. So we can see that this is evolutionarily stable, this one is evolutionarily stable, this is unstable. This is the Bayesian of attraction of this equilibrium, and this is the Bayesian of attraction of this equilibrium. Okay. And here, well, everybody wants to go to cooperate, because if they know that if I cooperate, I have a very high chance to get matched to a cooperator, then that's what's best for me to do. I'll use the same game under the trade group thing and show how dynamics work if we leave them there for 1, 2, and 3 generations. For 1 generation, we get the same result as before, right? You get the bad equilibrium, where nobody cooperates. If we leave them in the trade groups for 2 generations, then we have, this starts becoming, this is an equilibrium now, 0 is an equilibrium, and we have a mixed one, as before. And you can see that this is the mixed strategy, which is not stable. And as we increase the number of generations that they stay in their trade groups, the Bayesian of attraction of the good equilibrium, the cooperative equilibrium, increases. Okay. Now, let's do some comparative statics. Here is the index of associativity, and we see that for small, and these are the equilibria. So for small values of the index of associativity, we only have the bad one. After a certain point, then you start having the other one, and the intermediate one, which is unstable. So you can see that the Bayesian of attraction increases as associativity increases. So after a point, actually to cooperate becomes also risk dominant, in the sense that if the 50-50 population will be attracted to that. Okay. For the other, let's do some welfare. Let's look into welfare in this game. This is equilibrium welfare. So if these states, so this is the proportion, again, it's x, is the proportion of cooperators. And as we increase, if the equilibrium is closer to 1, right, so that the whole population is cooperating, welfare increases. This is what we can say, right? So the best thing here would be that, which I will contrast with this case. So if it is better to have two CD groups than to have them segregated, dynamics change, which is interesting. So, of course, for zero sortativity, you have only that equilibrium surviving, but then you get a very different behavior than before. Suddenly, the middle equilibrium, the mixed one, becomes evolutionarily stable. So dynamics would lead you there. So you can see it's negative here, so you would go back, and dynamics are positive here, so we go here, and this is evolutionarily stable, and these two are not. And the interesting thing is that in the trait group models, you get the same behavior for some games. So we have this and that. So this is still in the same situation where you would rather have them, if you're looking into sum of things, right? Sum of pairs. You would rather have them mixed rather than segregated. You still get that one. But for a different game, you get very different dynamics. Right? So we still keep the same condition, but we get dynamics like before. So this one, we have the two stable equilibria, the end, and an unstable in the middle. So it doesn't. So the trait group mechanism doesn't exactly apply a constant index of assortativity. It increases assortativity, of course, but it's not constant for all states. Right? So we can get different dynamics. Again, some comparative statics. As we increase assortativity, we get from we have always a unique equilibrium. Right? Under the constant index of assortativity, we always have a unique equilibrium. And that is evolutionarily stable. And this is how it goes. Now, welfare. Of course, now it's very interesting that if you had that state, right? For example, you can see that this is very high, right? This is what you could get if you matched all the population in the mixed groups. If you played the normal form game and you had this mixture of the population and they were matched at random, this is the payoff they would get. But under the matching rule, you don't get that because you get lower welfare because you're getting good people with good people. Cooperators with cooperators and defectors with defectors, which decreases welfare in that sense. But so this is very hard. You cannot attain it. Right? But again, the evolutionary optimum in that case would still be that. Right. Now, let me conclude. What we did is that we generalized the concepts of ESS to allow for more complex population interactions and to have any kind of matching in very general sense. And our formulation captures standard group selection models, such as a haystack and trait group model, as I showed before. And we proved the welfare theorem for evolutionary models with non-random matching. So an evolutionary optimum can be attained if we appropriately choose a matching rule. So what to take home would be that we have an overarching model in the sense that we can study both natural biological evolution or evolution under some institutions. So we can study both nature and society. And it's also optimistic. If we can get something to be a steady state, we can get it as at least as a Nash equilibrium under some matching rule. And that's it.